Boom.
Right, in this video, we're going to do something that may seem like, oh, where's the algebra, where's all the problem solving? But what we're going to do is train you to start thinking about how much. So energy, how much? It's an important thing. Good engineers, good scientists, applied scientists, they get a sense of how much. And those that just do book learning kind of books, textbook problems, don't learn that, and it's not good. You need to know what's reasonable, okay? So let's talk about this real quickly. Quick review. Entity. You know, I define the word entity. Maybe you can come up with a better word, but it's a little provocative, and that's good. I say entity and entity, something that exists in space-time. It's matter and light. That leads to other good questions, like what are the particle physics force carriers? What's that all about? What's it mean? What's string theory? What's dark matter? What's dark energy? Good, those are good questions. So this isn't like set in stone, but around us we have matter and we have light. So we can think in terms of that, and that's a great start for quite a while. Okay, so entity, right? Interactions, there's interactions between entities. Light can bounce off of matter. Matter can glow, we're all glowing infrared. Objects can hit, so there's interactions. We talk about forces, that's an interaction. Mass is not an interaction, right? It's a property an object has, so we got properties. Properties that we calculate from measurements, right? We can calculate this from measurements. So there's mass, there's momentum, there's energy, there's electric charge, and on and on. These are things we take measurements and we work within our theory to calculate these properties that these entities can have. Okay, cool. Just wanted to say that. Now let's get on with energy. So we're talking about energy. Energy, as you know, I defined as the ability to cause changes of any sort. I think that's a really good definition to work with conceptually. There's various types of energy, as you saw, and we'll look at that more closely in a second. An object's energy can change form. This is an important idea, from one type to another, right? You probably know kinetic energy and potential to kinetic, and we'll get into that in a second. So energy there's types, energy can change form. So when I say types, there's different ways that an object can hurt you, reasons that you're worried about it, okay? And it'll change form. Energy can be transferred from one object to another through collisions or someone hitting or me throwing something. Energy can be transferred from one object to another. Okay, so you can lose energy, right? You keep pushing something all day, you're going to get tired. And light can give or take energy. Give energy to matter, take energy from matter, and we'll deal with light's interaction with matter later. So yes, it's an issue. And yes, I am glowing infrared. And it's probably because we're at the end of our spring break, and Travis has been graceful and gracious enough to come in, and we're still sporting the spring break time. It's the end of spring break. We still got a lot of energy. I had to race to get here, so I used energy, and I shaved too fast and cut up my neck. So energy, it can hurt you, it can heal you. All right, that's energy conceptually. Now let's go over here and let's do some types of energy, define it mathematically. Later we will derive these, okay? But first let's get the game. Let's get how we do this, and we'll take a look at how much. All right. So first, really, really important idea is that energy is a scalar. Okay, energy is a scalar. With vectors, direction is specified by plus and minus. Minus is just the opposite way from what you decided to call plus. Here, you don't have direction. It plays in, but ultimately energy, it isn't a directional thing. So you don't decide which direction is plus, you decide where E is 0. Now that's weird because we think if you have no money, you have none, right? But now 0 is not none, we're going to see. It's just a reference, okay? So we're going to set or choose where or what we mean by energy is 0. It doesn't mean none, right? That bugged me when I was learning it. Plus then means energy is more than 0. More energy than 0. Minus is less than 0. That's all it means. So we're going to talk about that and explore that a bit. And we will also see that energy in itself is a relative term. But change in energy is physical. Got it? We'll explore that. You'll get it more and more. So the amount of energy is not really what's physical, it's how much it changes. And so we're free to call 0 the 0 reference. It's just shifting our number line. Okay, let's explore that a little bit. I see I have a typo. Kinetic energy. All right. So there's these types of energy. There's kinetic energy, energy of motion, as you know. We know translational. Now, translational is kind of a funny word. If you translate one language to another, you're kind of used to that word translate. If I translate an object's position from one place to another, that is moving from one place to another, we call that translational. There's the definition or the equation for that is 1/2 the mass of the object times the speed squared. Notice there's no vector in here, right? So that's the speed, and the speed is relative to v equals 0. So again, you're traveling on a train, then this object relative to you has 0 velocity. You're not worried about it hurting you. On a plane it does. So that's the definition. Now, when you get to relativity, quantum mechanics, these things, these definitions have to change, but it works pretty well in standard things. There's rotational kinetic energy, energy of motion by rotating. So things that are rotating have energy. They can slap you, right? They can move and they can hurt you if they're spinning fast. We'll get to that later pretty soon. Next, there's potential energy. What's it the potential for? It's the potential for kinetic energy. So if I lift something up and it's going to drop on my head, it's got potential to start moving faster and faster and hit me. So how much potential energy does it have? We're going to talk about some subtleties again with this later as we derive it more carefully after we do our introduction. So we've got potential energy of gravity. We can use uppercase g or lowercase g. Potential energy of gravity is the force of gravity times the height, or mg times the height. Notice that there's a force here involved. So inherently, actually, potential energy is an interaction. Again, we'll get to that later. The amount of potential energy, not physical. The change is. So what we do is we set where h is 0. You can choose anywhere you want to be h equals 0. Above that line is positive, below is negative. Okay? So that's that. I can choose this to be h equals 0. And then if I take an object, maybe a baseball, since it's almost baseball season when I'm videoing this, that's more than 0. That's 0. That's less than 0. Still, if I drop that on my toe, I feel something. Or I can do it, change my h equals 0, and all of a sudden it's negative. Now it's positive. Now it's 0. So you get to choose, and all that matters is that you work it out consistently, because it's the change that's going to matter. No matter what I say, if I drop it from here to the ground, it's still going to fall from here to the ground, the same amount, independent of where I set h equal to 0. So realize that. More than that level is positive, less is negative. And another very important point, with vectors, the direction is given by plus and minus. Here we're talking about the amount. So with vectors, I could choose plus to be up, and then down will be negative. Maybe you want that plus y. I can also call this plus y here. Now some say that's too much for people that are just being introduced to it, but I think it actually makes it easier for you. You can call that positive y. Choosing coordinates is a very important point, right? We sometimes tilt our coordinates and we do different things with our coordinate systems. Right? But no matter, if I call that positive y, this is still more height than this, right? That's more than this. This is less, right? So independent. So I like to use mgh rather than mgy. Y is kind of tied to a coordinate system. But if you are using y, you're inherently saying that that's positive, because this is more than that. All right, key point. Now, there's the elastic potential energy, or ideal spring. We'll often write spring, but remember it's an ideal spring. It's a linear spring. It's a Hooke's law spring. You saw that in the force videos. What's the equation? Well, it's the force of the spring, average, times the amount stretched or compressed. I do like the lowercase letter s, because it doesn't matter whether it's vertical, horizontal, or anything. That's kind of a nice thing for the amount of stretch or compression of a spring. The average force then, since it's linear, is 1/2 ks times s. or 1/2 ks squared. Again, we're going to derive that carefully later, just go with it for now. S equilibrium is where we set the 0 point, okay, for that stretch. No stretch there at that point. Also, there's jiggling energy, which is thermal or sound energy. So any jiggling that happens. All right, so the jiggling energy will come in later. If I take this guy, my fingers, I have energy of motion. I can go up, I can go down, I can move. But there's also jiggling within my fingers. And as I mentioned before, I'm actually radiating. All things in here are glowing infrared. So there's light given off, right? And we can absorb infrared, and we can do a lot of different things. So we'll get into that later, but I can transfer my thermal energy of my atoms. Well, I was able to earlier. Let's see. That's interesting. Speed them up. It's not doing it. Okay, that boils and bubbles. You can try it another time. Anyway, you can touch things, you can make them speed up, and that's jiggling energy. You can create sound, that's jiggling energy. So there's a lot of energy accounting that we're going to be doing here in just a moment. Want to make a mention here for later because it's kind of a confusing abstract concept. Potential energy. We will soon see that their potential energies are associated with what's called conservative force. Don't overthink it right now, we'll get to it. Conservative force, the introductory thinking of it is, if a conservative force takes energy away, then that conservative force will give it back. Right? Gravity. If it slows an object down, it'll speed it back up, if you let it, of course. A non-conservative force, NC, doesn't give it